Recording in progress.
Okay, it's going to be interesting. I can remember where to go next. So in the first half of the class, we will see a little demo of some of the ideas we discussed last time, which is related to propagation of pulses or transients in a transmission line. So I have here an oscilloscope and a function generator. Okay, so just give me 2 minutes to make a basic circuit. I'll draw that on the board and we will then discuss what should happen and then see what happens. Sorry, this is doing something strange. So I have an oscilloscope here. I have a function generator. Okay, so this is just something which is going to generate some waveform, and this is the oscilloscope. I have taken the output of this guy, and if you see what I've done here is connected one of those things I said they're very bad, this T junction thing. It's really just three transmission lines connected at one point. Okay, but they are very short sections of transmission. So I've connected a T to the oscilloscope, and I've connected this wire here. And right now this is just open. And from the function generator, I'm going to create a pulse which repeats at some slow rate. Right now, I think it's set to about 1 megahertz repetition rate. So from here to here, this is going to be like 1 microsecond. The pulse width itself is about 20 nanoseconds, and it has a rise time and a fall time of 9 nanoseconds. That's just the instrument's capability to generate sharp pulses. So now you can see this light. First row is board and board on. Okay, so here. So you can see the expected pattern over there. If I zoom in, you can see one of it. Let me zoom in again. The scales are not clearly visible, but it's 10 nanosecond per division is the horizontal axis, and the vertical axis is 1 volt per division. So right now you're seeing there are two divisions it crosses on the vertical axis. So it's going from 0 to 2 volts, and it's roughly 20 nanosecond in width. Of course, there are these rise and fall times, so it's rounded. Okay, so if I zoom out now, you see the second pulse, and right now the horizontal division is 100 nanoseconds per division. So you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so 10 division, 1 microsecond. Right, that's what we have set up, and that's what we are seeing. There are questions you can ask about why is this empty part. So remember, the T junction is not connected fully. So if I go back to the diagram, this part is currently left unconnected, but currently it's not doing anything because this length of transmission line from here to here is very, very small. So strictly speaking, the wave which is coming here should split into these two, and one goes here, the other one goes here, but that reflects back and it can do something funny. But because this is very short, you're not seeing the effect of that. But this is what we will change as we go along. This oscilloscope has one setting which actually allows me to change the input impedance of the instrument. So remember, in microwave frequency, we always have source impedance as 50 ohms and load impedance at 50 ohms, ideally speaking. On the lower end of frequencies, because remember, right now, the repetition rate is only 1 megahertz and the pulse width is about 20 nanoseconds, right? So if we invert 20 nanoseconds, that's about 50 megahertz, right? So this instrument actually has only a bandwidth of let's silence this. What was I saying? 50 ohms, right? The load impedance ideally is 50 ohms, but because this is actually a low frequency instrument, both the signal generator and the oscilloscope we are using for this demo are actually on the lower frequency side. So it's possible to have electronics which has high impedance. The reason high impedance is always used, this is because of if you go back to your ideal voltmeter picture, you want it to be infinite impedance so that it does not perturb the thing you are actually measuring. But at high frequencies in microwave range, that's just not possible. Okay, so this is low enough range that it actually provides you a setting. So I can actually choose the oscilloscope to either have 50 ohms to ground or 1 mega ohm to ground. So I'm sure many of you must have played with oscilloscopes, and these settings exist in some of them. So right now it's actually connected to the 1 mega ohm setting, and that's actually the reason why the voltage is going from 0 to 2 volts, even though I have set 1 volt peak to peak amplitude here. Okay, so it's a slight digression here that instruments which are designed in this slightly intermediate frequency range, you will have this option. Even this instrument actually asks me, what is your load? Is it a 50 ohm load or is it a high impedance load? And actually it doesn't change anything. Its output impedance is always 50 ohms. It just tells you the number which you expect to see on the load. So let me just quickly explain that, and then we'll continue with the demo. The point is that the source has a 50 ohm source impedance. Okay, this is 50. And in a conventional microwave setup, you always have a 50 ohm load. So in order to make it convenient, the instrument actually displays the voltage that would be dropped across the 50 ohm load. This is actually the reason I'm telling you that this is a convention. When you take a microwave source and it says power output 0 dBm, or 1 milliwatt or something, that power is referring to the power which is actually going to be dissipated across a 50 ohm load which you have kept here. Why am I making a big point of it? It's because in order to get a certain power here, the voltage here is not going to be corresponding to only this voltage drop, right? Because there is a factor of 2 division. Whatever voltage you have here for this ideal, this is your source. For this ideal voltage source model, this voltage needs to be twice the value you need here. So this is more on the practical side of things, that if you deal with these instruments, it can actually cause mistakes if you're not careful about the setting. So these instruments, they try to make it convenient for you that if you're working in an all 50 ohm system, it will give you the voltage or the power that is dropped across the load. However, instead of connecting a 50 ohm load, if I connect an oscilloscope whose input impedance is 1 mega ohm, then you're actually no longer getting this division, right? So it's 1000, 1 million over 1 million plus 50, which is basically 1. So you will measure the true voltage, which is actually here. And this can cause serious mistakes. And this is something which happens in the labs all the time. So this is just something, a little digression to mention this. I have set the instrument to 1 mega ohm, sorry, 1 volt peak to peak here, but I have not mentioned that the output is high impedance. So you can actually make both of them compatible. Right now they're incompatible because this is expecting a 50 ohm load, but I have actually put a 1 mega ohm load. The difference is that in the instrument, when I change the output load, it's just a factor of 2 multiplication in the display. Nothing is changing on the back end. The impedance of the source is still always 50 ohms. Whereas when I change the input impedance of the oscilloscope from 50 to 1 mega ohm, it's physically changing. So the signal which comes here will experience a different load across it. Okay, that's important to know because that will determine whether things are matched or not. So I'm going to put this back, show you that if I now, so it's actually this setting here, which unfortunately is very difficult to see with this. It's this setting I'm changing, this one here. Currently it's set at 1 mega ohm. And if I put it to 50 ohms, you see it drops by a factor of 2. See exactly 1 box. Okay. I'm going to leave it at 1 mega ohm because it's actually convenient for this particular demo, because I can now probe this area without changing too much about what's happening with the rest of the transmission line, right? So we will leave it at that and then make some changes to this and see what happens, okay? What I'm going to do now is I'm going to connect a cable here, which is sort of a long cable. Okay. I think for the people on the camera, here is a very long coaxial cable. We will learn more about this a little bit later today. This particular cable is called an SMA cable, which I think stands for sub-miniature adapter. That's just some random names, has some history. I've forgotten what that is. But this is a long cable, and I'm going to connect it over here. Now, because both the oscilloscope and the function generator use a different connector standard, which is this one. It's called BNC. I'm using a BNC to SMA adapter to go between these two things. These two different series, BNC and SMA, basically differ in size. BNC is bigger in size, larger cable, larger connector, which also means that it doesn't work to very high frequencies. So this is the simple naive argument here, is that high frequency means small wavelengths. So things have to be precise at smaller dimensions. So you need usually thinner cables, smaller connectors for high frequency operation. BNC is the standard cable most of you have seen, like this type of cable you use in your labs all the time. You don't think about it much when you're doing signals at DC and low frequency, but this is also a microwave transmission line. Inside this cable, there is a center conductor, which is the active part, and then the outside ground. So it's both of both this cable and this cable have the same coaxial structure, but they are made differently with different sizes. Sorry? The diameter of the cable. So both the outer diameter and the inner diameter. We will look at this in more detail in just 15-20 minutes. Okay, so I want you to now pay attention to the original signal. And just to remind you, it's going from 0 to 2 volts. Okay, I'm going to turn it off and connect this cable because we'll first try to predict what we're going to see. Okay. So I've connected this cable here. You can see that at the T junction, there is this cable now going over there. All right, back to the scope. So, any thoughts on what we should see? Oh yes, so good question. The cable here ends just in a open circuit. So it's not, I have not put anything here. So it's currently, we can treat it as a open circuit. This one goes up or down? Or this one actually side ones don't move. So remember, initially it was 2 volts. And we saw a pulse which is repeating once every microsecond, right? So what do we expect? So this signal here is going this way. Now it encounters this T junction, but the oscilloscope is set to 1 mega ohm input impedance. So let me give you a hint. That means that we can actually forget about the oscilloscope as being part of the circuit. Its job now is that it's telling you at this particular value of C. So if you imagine this whole thing as a transmission line, a single continuous transmission line, this T's job and the oscilloscope job is actually for you to measure the voltage at this particular, whatever Z equal to L. If that's the length from here to here. So what do you expect to see? So in some sense, this is now behaving like an ideal voltage tap at that particular point. It's not participating in the actual transmission properties. In some idealized sense, there is always something going to happen, but it's good enough for this. Just think about it for a minute. I'll be back. Hello? Anybody? Priyanka?
So in the oscilloscope, maybe we would see 1 volt till some time t naught. and after that it will directly become V, well, 2 volt here.
You will see 1 volt for some time. Why 1 volt?
I'm thinking that the characteristic impedance of the long wire is 50 ohms.
Okay.
So I mean, it will be similar to the case that we saw last time.
Okay, good. So what he's saying, so the difference between this disconnected, it's hard. And I just wrote on this board like 5 minutes ago and I can't erase it. It's really terrible. Like this, like. So if we sort of ignore the time aspect and the length aspect of the cables for just a second, just to illustrate the point which Gaurav is making, the source is a 50 ohm source. Okay, so this is 50 ohm. When this cable was not there, all it saw was a mega ohm load, and hence it measured the true voltage which is generated here, which is twice of what is mentioned on the screen. So that's why it's 2 volt. Now, when we have connected this cable here, that's equivalent to putting another 50 ohms across it, right? But again, momentarily in time, because this is the cable is not terminated on the other side. But remember that the scope signals are local in time. When we see a certain voltage rise and fall, that is happening at that particular time. It's not here, there's no steady state picture in the same sense. Okay. So the moment you put a 50 ohm here, the voltage drop across these 2 points becomes half of what it was before. And that's the same voltage drop that's going to be across the 1 mega ohm as well, which is what the oscilloscope is going to display on the screen. Okay. So what Gaurav is saying is that the voltage will be half is correct. But what's going to happen after some time? And what is that time? Gaurav?
So since this is a pulse, this should drop back to 0, and the pulse will traverse the whole length of the cable and then come back. So it should again be, I guess, 1 volt.
Okay.
I'm changing my answer here. So since this is not a steady state, so the pulse goes, we see 1 volt, then the pulse comes back, we see again 1 volt.
Did you guys follow that argument? Any thoughts on that? Yeah, I mean, it's drawn in front of you, right? So what's going to happen? So the pulse arrives from the function generator to the oscilloscope first time. And at that time, the scope will display a pulse. But now half the amplitude of what it was when that extra cable was not there. And then what happens? Okay. There is some?
There'll be some interference because
Interference between what?
the incoming pulse and the
Okay, but the incoming pulse has already reached this point. The next pulse from the function generator can in principle come or never come as well. I have set it to 1 microsecond. So it's actually quite far. I don't have a cable which is long enough for me to have 1 microsecond time delay. So what will I see on the oscilloscope after, and what's the time? What's the next event is going to happen at what time? What determines that? Which cable? This extra cable, right? So this pulse is now, because this tap is not going to do anything to it, it just propagates along here all the way to this guy. Open end reflex, comes back. We'll reach the oscilloscope again. So the oscilloscope will show another pulse, which is time delayed from the same pulse which arrived a little while ago. And the round trip time will be twice the time to go from 1 to n, right? Because it's has to travel twice. And then what happens? So let's forget the next pulse, which is a microsecond long. Then this pulse is going in this direction, same amplitude hopefully, and then comes here. Will it reflect here?
Do we take input impedance of the function generator to be infinite?
Can a voltage source have infinite input impedance? Voltmeter, ideal voltmeter has infinite input impedance. An ideal voltage source has zero input impedance. But this is a 50 ohm system. So remember I said that the function generator is always a 50 ohm source in this case. Even if I set the output load, it just changes the display. The source here is always 50 ohms. This is always 50. So this is matched. So that pulse, once it reaches here, will no longer reflect. So the cycle ends. There's only one set of things going on. So pulse travels from here. Amplitude now half of what was before. It's measured here by the oscilloscope. Oscilloscope displays something, a pulse. This travels all the way. There's some time delay. And then you come back. And that's it. But some time much longer, a second pulse will come, but that's just because this thing is set to repeat itself at some rate. Okay, so let's see. Turn it on. So notice it's now half, right? Only one box, not two boxes. It's 1 volt, exactly as we predicted. In fact, there is some interference because this cable is not long enough. So what is it telling you? You can see the second pulse. So let me zoom in to this a little bit. Okay, so you can now see that they're both almost the same height, which is what we expect, but they overlap. What does that tell you? That the time of the pulse rising and falling is longer than the round trip time for the pulse to go and come back. So that's why there is some interference, but again local in time. So it just adds at that particular point. So that's why the voltage here is just like slightly higher. Okay, we can fix this. Here is another cable. I have an adapter here to connect it to the original cable. So I'm going to connect this. So it moved a little bit to the, now they no longer interfering. So the first pulse ends and then the second pulse starts. That's again just purely a function of the length of this cable. I could make it even longer. Let me see if I have something to make it even longer. No, I don't. Yeah, it's okay. All right. Now we can also see the effect of the boundary condition. I'm going to the end for the remote people who can't see what I'm doing. I'm going to the end of this longer cable, which is still just left unterminated. And I'm going to put a termination there. Okay. Actually, I don't have an additional adapter, so I'm actually going to disconnect that additional cable. Doesn't matter because you can still see both the pulses. Okay, so it's come back together. And what I'm doing right now is I have a this little thing here, which is a 50 ohm load in the SMA format, so that I can just screw it on at the end. And I'm now changing the boundary condition from being open to being matched. So the reflected wave is now gone. So the one which travels all the way to the end is no longer coming back because it's hit a matched load. I take it out. Let's come back again. We will try one more boundary condition, which is a short circuit. So I'm just taking a piece of metal and shorting the center pin in the ground. Oops. Oh, come on. So you see that the sign flips, right? Obviously, this is not a very good short circuit, but it does a fairly decent job at low frequencies. Okay, let me show that one more time. Open end, short end. It kind of looks extended because they're overlapping a little bit, but you can see it's almost exactly the negative of the first pulse. So this is because the returning pulse is now coming back with a different phase. Oh, just the so all I did was the SMA cable here. There's very little light here. So this has a center pin and a ground. So I just connected the two of them with a screw, which is not really a true short circuit. But what does that mean? Basically means that it's not a true short circuit at very high frequencies. But this entire experiment is limited in frequency anyway, because this guy cannot create frequencies beyond 30 megahertz. This cannot measure frequencies beyond 100 megahertz. So it works as a reasonable short circuit. And especially for the phase, the fact that it's flipping the phase, that will always work as long as the impedance is below some value. So you will see the effect very clearly, as we can see that here. Okay. That was the last thing I was going to do. I'm now going to change the oscilloscope from a 1 mega ohm system to a 50 ohm system. Okay, that means that this also becomes 50 ohms. Now what will happen? So the best way to do it, again, start from the beginning and go through the, as a function of time, what happens. That's the best way to figure out what the result is. So again, so oscilloscope's job is that whatever voltage is dropped across its input resistor, that displays on the screen. That's what it does. So that if you calculate that, then you know what it's going to do. So it was 1 mega ohm. Now I'm going to have it as 50 ohms. So what happens when this pulse reaches this point? Become 1/3.
We take the effective resistance that point to see effective.
Yes. So over here, this will now become 25 ohms. And the voltage drop across both of those is the same. It's going to be 25 over 75, be 1/3 of the original signal, and 2/3, or sorry, 1/6 of this value, right? Or no, not 1/6. It was already half. So we have 2/3 of the current value. Because this is already V by 2. What we are seeing right now, I mean, we just saw these amplitudes are already V by 2, where V is the source voltage. And now we said that the new pulse is going to be 1/3 of the original value. So it's going to be 2/3 of this value. Let's see, I'm going to change it. You can sort of see it's. Let me go back to, I've changed the scale to now 500 millivolts per division. So that's 1 volt. That's kind of 2/3, right? But what's going on in the rest of the screen? So remember, the cable right now is the shorter cable, the one which I connected first, and it's still terminated with an open circuit. But you're now seeing some other things showing up. Let me zoom a little bit more also so that we can see these things clearly. Can we explain this wave tray? Maybe I should make the cable a little longer so that it's actually, I have an idea. I just found a way to make the cable much longer, so we can see this a little bit more clearly. Okay, this is now even longer than what I had done before. Probably the total is 3 times the length. Turn it back on. So now you see it's a lot. You can see them all separated nicely in time, so you can see what's going on. Right.
So the cable is open end?
Cable is open.
The returning pulse is again seeing the effective resistance of 20 volts. Then we have again a 1/3 of, if you look at 50 and 50 of the input impedance of function.
Yep.
Then both the function limiter condition not matched. And then there's a reflection.
No. So I'm going to redraw this here roughly. Let me have the camera. So first pulse went here. We saw 2/3 on the oscilloscope. It traveled a long distance, came back. What he's saying is that at this point, again, there is a problem. The problem in the sense that there's an impedance matching problem, because this is a 50 ohm line, but it's seeing a 25 ohm load. 50 ohms because of the oscilloscope, and 50 ohm because of this line connected to the function generator. Which means that at this point, there's actually going to be another reflection and transmission. But the transmitted part can actually be forgotten. So the one thing you said was not correct is that the function generator is matched. Remember that the wave which travels here the mismatch only matters whether if this cable's characteristic impedance is different than the. It's not that there is a different load here. Okay. So the returning pulse here will experience a reflection and a transmission, but the whatever gets transmitted here is absorbed by the 50 ohm load, so that never comes back. So we can completely ignore what is happening to the transmitted wave. Okay. So the only thing which matters is what's going on here. So what you're going to see is that at this point, there's going to be a reflection, and the oscilloscope will measure a reduced one. So the next pulse you are seeing is the pulse which has gone back a second time, right? That's not this pulse here. So this is the first one which is traveling in this direction. This is the second one which is traveling in this direction. This one is the reflected wave of this guy traveling all the way back. So it of course takes the same amount of time. So the time gap between these two and these two is the same. But why is the sign inverted? Louder.
There is a 50 that sees a 25 calculated.
Does that make sense? For the wave which is returning back, the condition is that the source impedance is 50 ohms and the load impedance is 25 ohms, which is smaller than 50 ohms. So gamma is Z load minus Z naught over Z load plus Z naught. Whenever Z load is less than Z naught, gamma has a negative sign. And whenever it is greater, and infinite and short are the extreme cases. The reflection coefficient is not -1, but it's minus something which is a number smaller than 1. In fact, it's going to be exactly 25 minus 50 over 75. So it's the same fraction, but now the sign is opposite because the wave which came back, the pulse which came back and reflected with a negative sign. And then it travels without any phase change, comes back here, and then the oscilloscope picks it up and measured it. It also goes here, but we don't care about that. And what's the one after that? So now you actually have an infinite series situation, but each time the amplitude of the reflected wave is getting smaller and smaller by that factor of this 25 over 75.
So if you say what is that? If you said that one more PPT, so this is low.
Oh, okay. I'll come back to that. It's actually completely unrelated to this. Let's come back to that. So if we could see smaller and smaller pulses, you'll see that this will go on forever. Each time the pulse will have opposite signs. So except for the first time, because at this point, the first wave when it traveled here, that was the first time a pulse came from this direction. And that saw a lower impedance, but the reflected wave went this way, which we didn't care about. So that one would have, if we had looked at what came back on the instrument, you would have seen that the first wave would have also had a negative sign. But after that, the oscilloscope is only measuring what is happening between this point and that point. So only that thing is going back and forth. Whatever is coming this side, it becomes irrelevant. So that's why all successive ones. So this is positive because that's the incident wave. This one is just the transmitted wave coming back. And then next reflection, next reflection. Will keep happening like this. Yeah.
First, the oscilloscope measure, will it first time come back from that SMA input, and
You mean so first time back from here?
back from here, there's the second one side of first peak, right?
This is
This one.
this
So
is
1/3 of the first.
yes, no, of the
First.
1/3 of the first peak. No, it's 2/3, right? Because the first peak is already 1/2 of the original pulse.
My question is, so when it comes back to the oscilloscope and again gets reflects back, so it should be almost instantaneous. But why is there a gap between the second pulse and the third pulse?
You mean between this and this?
Yes.
One second. Okay. Let's walk through this again. This pulse, the first one, is when the pulse from the function generator arrives at this junction for the first time. This pulse,
And if it of the same height, that it aligns.
no. Well, you have to be more precise. Which amplitude? If I'm able to, if I check the amplitude here, then it's not. Because here, when the pulse is launched, for the function generator, it is seeing a 50 ohm transmission line. Right? It has no idea what is coming there because this is all local in time. So when the pulse is launched, it's launched from a 50 ohm source to a 50 ohm load. So the amplitude of the wave here, the height, is going to be V/2, when there V is the original source voltage. And if the oscilloscope was 50 ohms and nothing was correct, in fact, I think to answer your question, maybe we should check this because I am also slightly confused now with these amplitudes. I'm going to disconnect the long cable part. And this has resulted in, yeah. So the source is set to 1 volt peak to peak on, so, and that's the number it would expect to be seen on a 50 ohm load. So the oscilloscope is currently set at 500 millivolts per division. So you are seeing it's 2 boxes, so it's 0 to 1 volt. Okay. So 1 volt is the, you can say that 1 volt is the incident wave amplitude. And in this configuration, where you started from a 50 ohm source and ended on a 50 ohm source, you see a 1 volt signal. Now, when I connect this, the signal seen by the oscilloscope is, so remember again, so this looks like it's 2/3, right? It's slightly higher than half of that. So it's not 1/3 for sure. So where does that come from? Yeah. Yeah, but the thing is, in this picture, then I cannot compare it to the original one. But it's clearly, you can now see that that one is roughly three boxes, and this one is roughly 2 boxes. So it's roughly it's a little bit less than that. But that's because nothing is perfect and there are some losses along the way. But we need to check this number. See, the thing we were comparing is, for that I need to go here, right? I have to compare that, which is roughly 2 boxes on this one, which is 1 volt, and this, the first. So we are only looking at the first pulse. Okay, so after connecting, before connecting, so don't look at any of the other pulses. So this is roughly 2 boxes, and this is slightly more than 1 box. Okay, so where does this come from? So if the original wave here was V0, I mean this voltage source was V0, the matched voltage would be V0 by 2. Right? So V0 by 2 is 1 volt for us. But in this situation, the where you have 250 ohms in parallel, remember that this is still V0. Okay, so it's V0 into 25 over 75. So what you get is V0 over 3, but this is V0 over 2 into 2/3. Okay, it's slightly confusing, but it's just sequence of operations, right? True voltage source's amplitude is V0. Nobody ever gets to see that unless you measure in 1 mega ohm. Okay, that's what we saw when it was 2 volts. Match situation, which is basically when this was 1 mega ohm, we are able to measure the match situation. That's 1 volt. That is V0 by 2. Now, when we have 250 ohms, it's V0 into 1/3. But remember, V0 is the original V0. But the matched value was V0 over 2. So how do you go from V0 over 2 to V0 over 3? Multiply by 2. So that's why the first pulse now is 2/3 of the first pulse in the matched configuration, and it's 1/3 of the 1 mega ohm situation. So that's V0. That's V0 over 2, and that's V0 over 3. Okay, clear? So Panya, I also answered your question accidentally there, but the point is this. If you have a voltage whose ideal voltage source amplitude is V0 with a 50 ohm source impedance, and you measure the drop across a 1 mega ohm, you will measure V0. If you have 50 ohm, you measure V0 over 2. The instruments, because they expect in most cases you're working with a matched load, rather than you have to keep in mind this factor of 2, they allow you a setting where you can tell it, are you going to put high impedance loads or are you going to put matched loads? Currently, it is set to matched load setting. So it actually gives you the value of what is going to be dropped, which is actually V0 by 2. So V0 by 2 is 1 volt. But when I connect a 1 mega ohm, it will measure 2 volts. But I can change a setting here, which will actually not change anything to the voltage. It will just change the display to 2 volts. This is just for bookkeeping purposes so that you keep track of what you're doing. But I mean, trust me, 20 years, this causes confusion. If you're not careful about this, suddenly your voltages and currents are off by a factor of 2. All right, so hopefully this part is now clear. Yeah.
When you were disconnecting the peak was a bit higher. When you connected it, the first peak got a bit low.
Yeah. So in fact, let me bring this down here so that we have access to the full scale. I'm going to disconnect. I'm going to put it to 1 mega ohm. Okay, so right now it's set at 500 millivolts per division. Let's see if this will work. This is good. Yeah, the screen doesn't fit that. Okay, we go back to the previous one. Okay. 500 millivolts per division, 4 boxes, 2 volts, 0 to 2 volts. This is with a 1 mega ohm input impedance. So it's measuring the true V0. Okay. Now I change the oscilloscope to 50 ohm. It drops by a factor of 2. Okay. I connect the cable. The first portion is now 1/3 of the old one, and it's 2/3 of the second one, right? So because earlier it was here at 4 divisions 2 volts, then it became 1 volt, and this is like 0.66 volts, slightly lower because there's some losses and things like that. Okay, and if in this configuration I short the end, what's going to happen? So everything has become negative. Why is that? Correct. I was somehow expecting it to alternate, but let's just work it out. But that was happening earlier also, no? Everything was reflecting twice earlier also. Yeah. So, okay, first transmitted wave continues with the same sign, comes back with a negative sign. So the first pulse you see coming back has become negative. It has become negative. And that negative pulse, when it reflects here, becomes positive, and then it becomes negative again. So, sorry, this is correct.
Gap between second pulse and third pulse.
Yes. So there is no confusion here, right? So this is the first pulse which is going from the function generator to here. Yes. The second pulse is the transmitted wave going all the way to the cable end and coming back. The third pulse is the reflection of that pulse going all the way and coming back. So it's the same thing which is happening. So it's just like you have one long cable and the pulse is going back and forth and back. So there's no instantaneous part here. Okay. All right. So in the time remaining, we can now discuss these different types of transmission. So it's like I need a minute to figure out what to do. Okay, so I no longer do. Actually, I could do a spot in the first. So the most commonly used transmission lines when we connect instruments are going to be coaxial transmission lines. And coaxial transmission line basically has an outer conductor and a center conductor. So these are both metals. So this will be like some thin shell like thing. And then here there will be some dielectric. The thing I'm holding in my hand is an example of that kind of cable. What you see, of course, is just the outside, but the connector at the end, if you look at very, very carefully, let me see if I can focus it here. You can sort of see that there is a white colored thing. That's the dielectric for the connector part. And then there is a little pin at the center, which maybe you can see slightly. I'll just pass this around. You can take a look at it. And you can also see the other end of the cable, which is cut and exposed. Okay. So this, of course, is a cross-sectional view of the transmission line. If I just draw them like two parallel lines like we were drawing earlier, then one of them is the center conductor. So you have voltage of the center conductor with respect to the outer conductor at any point. And then the currents are flowing through this. So which means that here, because there is a voltage difference between here and here, electric fields are radial, right? We have voltage difference. So electric field is radial along that direction. And because currents are flowing through the center conductor, magnetic fields are going around in circles. So if you now look at, imagine this is the center conductor and the current is flowing. So for a parallel straight line carrying current, you will have magnetic fields which are like this. Okay. So magnetic fields are going in this circular fashion in a plane which is perpendicular to the direction of the transmission line, and electric fields are going radially outwards. So if you notice, that means that the direction of the electric field and the direction of the magnetic field is always perpendicular to each other. So that's why the waves which propagate here, and I think in the next class we will look at this from the electromagnetic point of view in detail. This is called a transverse electromagnetic wave, or electric and magnetic wave. So unlike just a transverse electric wave or a transverse magnetic wave, maybe you might have heard these terms in your electromagnetic cases. This is called transverse electric magnetic wave. And the electric field is perpendicular to the magnetic field, and both are perpendicular to the direction of propagation, because the energy is flowing in and out of this plane. Right? So if you remember your pointing vector from your electromagnetism class, that gives you the direction of energy propagation, and that goes as E cross B, right? So here very nicely E and B are already perpendicular to each other. So the direction of propagation is perpendicular to that. So everything, and this is the most sort of ideal transmission line setup you have, because here the properties of the wave at different frequencies doesn't change much as long as you are within at low enough frequencies. So what do I mean by that? At some sufficiently high frequency, sorry, let me pause here for a second. What is considered small frequency or large frequency is basically related to the wavelength in comparison to the dimension of this cross section. We want the wavelength to be much larger than the cross-sectional dimension, not the length of the transmission line. Okay. That ensures that the overall cylinder doesn't allow you to fit some one wavelength or half wavelength in that particular thing. Those will now give rise to transverse electric modes. So this is called overmoding in a coaxial line, and that basically gives you the practical upper limit of where you can use. So for this type of coaxial cable, the one which I circulated to you and the one which is here, these guys, they have a outside diameter of 0.085 inches or 85 mil. MIL is a milli-inch. That's the terminology often used in machining. And that gives you like a cutoff frequency of usually around 40 to 60 gigahertz. So these kind of cables can be used to fairly high frequencies. The other fat cable, the BNC one, which is here, it has much higher diameter. So you can, if you compare these two guys, the black one is much higher diameter. Also, this doesn't have rigid metal inside. It's this braid kind of a thing on the outside, and even the center pin is like, you know, like a filamentary thing. So the BNC cables, the fat ones, they usually are spec'd only to work till about 1 gigahertz. Basically, beyond that, it's not guaranteed that the property as a function of frequency will remain flat, so your pulses will distort, will get attenuation and things like that. Whereas these kind of coaxial cables can go up to 60 gigahertz or so. I'm forgetting the exact number. I'll get that for the next class. In our lab, we mostly are working below 10 gigahertz. So these are more than good enough for that. A catch is the connector at the end. Okay, and this sort of comes under the entire category of transitions in microwave networks. So remember, in order to create this very long cable, I used a section of a cable. So this coaxial cable by itself, is a nice transmission line. You don't expect any reflections to happen while the signal is propagating through the cable. But here, you can have reflections, and in fact, you will have reflection. The reason is this small piece of connector is a small section of transmission line, but made with different dimensions. Right? It's bigger. Right? The outside diameter is bigger, and you saw in the there's also this white dielectric in the middle, right? And there's a center pin. But the characteristic impedance of this connector has to be the same as the characteristic impedance of the cable. So by using different choices of the dimensions, you've made a larger connector, because you can imagine that if I had a connector which was the same diameter as this one, it would be very hard to work with. They do exist. There are actually snap-on connectors which have a diameter very close to this cable, but they are much more expensive and more difficult to work with. So in order for the waves to propagate seamlessly from the cable onto the connector, onto this little extra piece here, which I had used to connect two cables. So let me show that on the screen here. Okay, what is this? This is called an SMA adapter or an SMA barrel sometimes. But what it actually is, it's just a piece of transmission line. Fatter, larger diameter, larger dielectric here. But this also needs to have a characteristic impedance of 50 ohms. So these are designed so that you can connect these two things and tighten them with like a screw-like action, and the wave is able to propagate seamlessly from there. So these transitions are actually a critical component of any microwave network. I'll show you some other type of transitions when you have to go from a cable to a circuit board. So the general principle is that everything is ultimately a 50 ohm transmission line. Their geometry is different, so you have to find a way to adapt it. Okay, and what is this adapting? The most sort of simple generic way of understanding is that if parameters change in some smooth fashion from one size to another size. So if you imagine that a coaxial cable like this slowly increased in diameter, right? Don't know how to do it, but if you imagine, but in such a way that the characteristic impedance always remains the same. So this is, I guess, slightly confusing now because I haven't told you how the characteristic impedance depends on the dimensions, but you know that it's related to the capacitance and inductance per unit length. So you can imagine that the capacitance per unit length is related to the distance between the center conductor and the outer conductor. It will be proportional to the dielectric constant which is used there. So if you're able to change the diameter slowly of both the center and the outside conductor in such a way that it always maintains the same inductance and capacitance per unit length, sorry, not the same inductance and capacitance per unit length independently, but the ratio of those two, then the wave will always see a 50 ohm line and it has no reason to reflect. These connections will always give rise to some finite reflection. So the whole engineering behind designing this is to ensure that they maintain they provide you the smallest amount of reflection as possible. So usually they will be specified, and there the frequency starts playing a role, because remember I told you the size is sort of directly related to, so fat things will not work at high frequencies. So that naturally means that this small transmission line which is used to connect two cables, even though the cables are thin, this will not work at a certain frequency while the cable itself might be okay. So you have to worry about all of these points here, okay? And there are some other rules of thumb that when you connect these things, there is a certain amount of torque you have to apply when you finish the tightening. If you leave it loose, then that impedance matching situation doesn't always come out. So you have special wrenches like this, which have a calculated amount of torque, and if you go beyond it, it snaps. So you don't want to over tighten as well because you could break, but you want to reach the right level of tight. So these are called torque wrenches. So you can tighten them and then it will basically click and then you stop at that particular point.
So the ends of the SMA cables, they have 25 ohm impedance. Sorry, 50 ohm impedance.
This? No. This is not an end. This is a transition from a 50 ohm coaxial cable of this dimension to a 50 ohm section of transmission line which has threads and pins so that you can mate it with another side. This is not a termination. There is something else here I had shown you, which is this guy. This is a 50 ohm termination, which is made to screw onto this, but this has a 50 ohm connected to ground. Okay, again, let me repeat. Characteristic impedance and load impedances are two completely different things. Okay. So this small piece of connector at the end is just a small piece of transmission line, but of a different geometry while maintaining 50 ohm characteristic impedance. Okay. So these are the most commonly used cables. They also come in flexible variety. So this is more like the BNC type of construction, but narrower. Let me show the remote, guys. Well, sorry, 1 second. I think I disconnected the USB of the webcam. So I'm talking about this. This is also an SMA cable, but it's a flexible variety. Whereas these ones, the ones you have been seeing till now, is called semi-rigid. Okay, they are made of metal, solid metal, but they are thin enough that you can bend them. Okay. There is also in the flexible but slightly fatter variety. This is also SMA, and they are larger diameter, so they usually don't work up to higher frequencies. But you see these black things at the end. This is called an armor. Its only job is to prevent you from bending the cable at these ends. Why does that matter? This is basically again related to the fact that what is considered a smooth change in the dimensions of the transmission line. Where is that cable which I passed out? Now this cable looks terrible, right? It's all because we have been using it for many years, it's been bent out of shape, but it still retains its 50 ohm characteristic impedance. You might think that if I bend it like this, something must be changing, right? Because what is the important number? The distance between the center pin and the outside dimension. Now you can imagine that if I'm doing smooth bends, it's probably still okay. So for a thinner cable, it's easier, but you cannot overdo it. If I just go all the way and create a kink there, like if the metal actually has a dent in it, then it's no longer going to be a nice 50 ohm transmission at that point. So you have to be careful about that. So with these flexible cables, this is a problem in the sense that when it's straight versus when it's bent, its properties will change slightly. Its electrical length can actually change a little bit. Now, this can be very critical if you're doing some kind of an interference experiment where different paths have to match up, and then suddenly somebody just knocked the cable and the cable moved a little bit and then the phases no longer match because the electrical lengths are different. So for all those things, semi-rigid cables are the best. These armored cables at the end, the reason they are is that they are a lot more sensitive to this at close to the connector. So if you bend it strongly here, its properties will change. So that's why they provide this kind of a protection, and they have also these other things. So that the bend is, if you bend it naturally, it will always bend with a smooth and a large radius, as opposed to like making some very sharp bends. In fact, let's see what happens. Okay. Hello? No, I think it's one of probably the remote guys who unmuted us. I'm going to try one last thing. I think we should wrap up because asset colloquium has to start. And I'm going to need some help to move this out quickly after this. Right. I have not tried this before, so this could fail, but let's see what happens. So let's go inside this corner. No. I think I probably removed the spotlight, so probably didn't. No, super. Like the one light I want is not. Okay. So pay attention to the distance between the pulses because that is determined by the length of this cable. Okay. And this is that bad cable which doesn't have any connector, but it's still like an open end. I'm going to attempt to damage this cable somewhere in the middle. Anything else shaking? And see if I can make it reflect. Seems like I can't really do it. Oh, actually, I just broke the cable. It's crazy that even it's like almost broken, but now you see that it's now come closer because it's quite amazing that even with this thing, I can make it behave as it was behaving before. It's strange. But you see, it's become shorter because I've damaged the transmission line here. So now you have a reflection here, but it could have some transmission which would then reflect at this other end and give you a more complicated picture. But yeah, now it's permanently damaged at that point. Okay, all right, so let's stop there. And can the two of you guys help me with this?